Hello students. In the last episodes, we discussed function and binary operations in detail. Today we study about the types of relations. Before that, I want to remark that sometimes we use the symbol x or y to designate the fact that x comma y belongs to R. So, it is as per convenience we use this and this with equal meaning. Now, if a relation R is defined in a set A is such that x R x for all x belonging to A, that is every element is related to itself, then we say R is reflexive. For instance, set of all lines in plane R space, the relation is parallel to is reflexive because every line is parallel to itself, while the relation is perpendicular to is not reflexive because no line can ever be perpendicular to itself. Similarly, the example of equal to, everything is equal to itself, so it is reflexive. The next point is the notion of symmetry. A relation R defined in a set A is called symmetric if x R y implies y R x for all x and y belonging to A. For example, in the set of all lines, the relation is parallel to is symmetric because if a line L1 is parallel to L2, then certainly the line L2 will be parallel to L1. Moreover, the relation perpendicular to is also symmetric because once one line is perpendicular to another line, definitely the second line will be perpendicular to first line. So, this way the symmetric relation holds for parallelism as well as perpendicularity. One more thing, suppose we take the relation equality in numbers, there also x equal to y means y equal to x. So, that too is symmetric. The next point is relation which are transitive. A relation R defined in a set A is called transitive if x R y and y R z means x R z for all x y z belonging to A. For instance, the relation is more than in numbers. If A is more than B and B is more than C, certainly A is more than C. Thus, is more than is transitive. Similarly, equal to, if A is equal to B and B is equal to C, certainly A is equal to C. So, even this relation is transitive. Again, take case of lines. Is parallel to is also transitive because if line L1 is parallel to L2 and line L2 is parallel to L3, certainly line L1 will be parallel to L3. If you take the case of perpendicular to, if a line L1 is perpendicular to L2 and L2 is perpendicular to L3, then it may not be so that L1 and L3 are perpendicular always, because we want everything always. So, perpendicular to relation is not transitive. Let us take an example. The question is, check if the relation R defined in the set 1, 2, 3 up to 6 by R is equal to ordered pair AB, where B is equal to A plus 1 is reflexive, symmetric or transitive. Let us check one by one. Here clearly, if you take A is equal to 1, then B is 2. So, 1 has relation with 2, 2 has relation with 3, 3 with 4, 4 with 5 and 5 with 6. But 1 is not having relation with 1. So, it is not reflexive. Moreover, 1 has relation with 2, but 2 has no relation with 1. So, 1 2 belongs to R, but 2 1 does not belong to R. So, it is not symmetric. Let us take one more problem. Show that relation R is 1 1 1 2 2 1 2 2 3 3 1 3 is reflexive, transitive, but not symmetric. It is given that R is defined in the set 1 2 3. Here 1 2 3 is the given set, and we have 1 1 belonging to R, 2 2 in R, 3 3 in R. So, every element is related to itself, so it is reflexive. It is not symmetric because 1 3 belongs to R, but 3 1 does not belong to R. So, it is not reflexive. It is transitive because we have 1 2 belongs to R, also 2 1 belongs to R, and 1 1 as well as 2 2 belongs to R. So, it is transitive. Next, we have a very interesting problem. In some class, a student claims that any relation which is symmetric and transitive will always be reflexive. Her argument is as follows: if A are B, then B are A by symmetry, and A are B and B are A implies A are A by transitivity, and hence R is reflexive. Question is, do you agree with her? The answer is no. Apparently, it seems that she is correct, but let us take example. X or Y means X Y is odd, where X and Y belongs to integers. Now, this relation is certainly symmetric as well as transitive, but it is not reflexive because 2 or 2 is not correct. That is, 2 2 does not belong to R. In fact, no element other than even number, other than odd number, is related to itself. Let us take one example. Let us say it be 1, 2, 3, 4, 5. We define R by x plus y is even. We can easily verify that the given relation is reflexive, symmetric and transitive. In fact, any relation which is reflexive, symmetric and transitive is called equivalence relation. Thus, an equivalence relation is one which is reflexive, symmetric and transitive. One more thing, here 2 has relation with 2, 2 has with 4, whereas 1 has with 1, 1 has with 3, 1 has with 5. So, this information divides this set into two subsets, namely 2, 4 and 1, 3, 5. Now, these subsets of A has the property that any two elements of the set is always related and no element of any one of the set is related to any element outside this set. So, such a subset is called equivalence class. Thus, an equivalence class induced by an equivalence relation is a subset of the set under definition such that any two elements are always related and no element of the set is ever related to the element outside this set. We have to write down all the equivalence classes for the relation R defined in the set of integers by x or y, meaning thereby x minus y is a multiple of 5. First of all, we must show that this is equivalence relation. Now, x minus x is always 0 and 0 is multiple of every number. So, this implies x r x, that is R is reflexive. Then x minus y is equal to minus y minus x. So, whenever 5 divides x minus y, it will also divide y minus x. This implies x r y implies y r x. So, it is symmetric. Then, if x r y and y r z, that means x minus y is 5 k, y minus k is 5 m, which gives x minus z. X minus y is 5 k and y minus z is 5 m, implies x minus z on adding this 5 k plus m. Therefore, x minus z is also multiple of 5, hence x r z. So, R is also reflexive. Thus, we have seen that R is reflexive, symmetric and transitive. So, it is equivalence relation. Now, coming for equivalence classes, let us take the example of 0. Now, 0 has relation with 0, plus minus 5, plus minus 10 and so on. So, the equivalence class containing 0 is merely this set, that is 0 plus minus 5 plus minus 10, that is all multiples of 5. Now, 1 is not appearing here, take 1. Now, 1 has relation with 1 itself, then 6 and minus 4, 11 and minus 9 and so on. Similarly, we will have 2, that is 2 relation to 2, then 7 minus 3, 12 minus 8 and so on. Then we have 3, that is 3, 8 minus 2, then 13 minus 7 and so on. Then we have the element 4, we have 4, then 9, then minus 1, then we have 14, then minus 6 and so on. Now, if we take up 5, because 5 is already there, so no more new classes we get. So, there are exactly 5 classes which are equivalent classes for this relation. This completes the problem. Now, dear students, Today we have completed the discussion on binary relations. There are three types, namely reflexive, symmetric and transitive, and when the relation is having all three properties, we call it equivalence relation, and for equivalence relation there brings up something called equivalence classes. Thank you very much.